Hello everyone, my name is Max. This is my second lab, motion of a falling object. So for this lab we were supposed to find some kind of object and record its motion as it falls. Um, I chose to record a ping pong ball as it fell from about 3 meters. This is my friend holding the ball, releasing it. It runs for about zero point 0.8 seconds and I stopped it right before it hit the ground. Um, so basically we're using Newton's second law within a Python code to try and simulate this motion again. And we have two different models this time, one with a drag force and the force of gravity, and then one with just the force of gravity to try and see the impact of that drag force on the motion of the object. Um, so to my model, um, you can see here, this is my model, pretty standard. I commented out the parts that involve the drag force here, this coefficient b, and that information gets put into this F net equation. So when b equals 0, it pretty much negates the drag force, and you can see that there. As I say here, my b was chosen basically to approximate the final position of the observed data. You can see that here, trying to get it all about 3.29, 3.3, somewhere in that area. So that's where I selected my B. It was very small, so it may not have been entirely correct, but it was the best for that approximation. Um, so as you can see here, these are my results. This is the graph I obtained after plugging those numbers in. The observed value is the blue line, and you can see the two models on the right. The model without drag force severely underpredicted, well, not severely, but underpredicted the motion of the object. We could see in the model here that accounted for drag. It kind of helped a lot to make it more in line with the observed values. So there definitely was drag acting on the ball that affected its motion. Um, Otherwise, it would have resembled this line more closely. And so, what does this mean? An object reaches terminal velocity when the force due to gravity equals the drag force. They're each pointing in opposite directions, so it's not accelerating anymore. It's moving at a constant rate. If we go to my graphs of the motion, you can see they're still pretty curved. There's never really a point where it's moving without change. I don't think it actually reached terminal velocity. I think it needed to move a lot farther to reach terminal velocity, actually, because it only moved 3 meters. So I think if it was given maybe 20 meters, it could have reached it, and it would be more pronounced, like it would be a linear line instead of the curvature we can see in here. So if I were to give this object an initial velocity instead of dropping it from rest, then here we can model that with the code, actually, the Python. I lost it. You can see here that it's very linear. I gave it an initial velocity of 10 meters per second in the negative y direction, and printing out the values, you can see there's not really, it's pretty consistent between the values. There's not really change. So I'd say it reached terminal velocity with that input. Basically, because the terminal velocity is dependent on the drag force equaling Fg, and the drag force is also dependent on the velocity of the object, or the square of the object's velocity. If it has an initial velocity, it's going to reach that value faster than if it didn't, because it has to accelerate through that value over time. So the case with an initial velocity will reach it quicker, but they'll both eventually get there if it's given enough time to fall through the displacement.